Thank you. Yes, my background is more in the epistemological side of philosophy of science, but I think there are useful concepts in the structuralist view on theories that might be helpful to flesh out, define some fundamental concepts from the scientific realism debate. Yeah, so my talk, I want to first begin with some introductory words on structural view on theories, what it is. Also introduce already some kinds of formal concepts, and then I will go through 3 different lessons that are more or less independent of each. So if you get lost at one point, you can get back into the talk of the next lesson. The first will be a proposal to define what approximate truth might be in a formal sense. So I will use admissible blurs from the structural view theories. The second lesson will be a formal definition for limiting case reduction theories. I mean, it's very important in the epistemical debate, but also in scientific realism debate. Yeah. And then in the end, I will give you, I mean, at least a sketch of an argument for an instrumentalist view on scientific theories by pointing towards the indispensability of idealizations in our theories. Yeah. Okay. So, if you know anything about the structural view, possibly the slogan coined by Patrick Serpice to axiomatize theories to define a set vertical predicate. So basically, if you want to have a rational reconstruction of a theory in the structural view, you simply have to write down the axiom as a set vertical predicate, more or less what you have done in your presentation already. So we don't have to care about observational or vocabulary, about any rules of inferences. Can directly start with our axiom, and we are almost done with our reconstruction. Yeah? So then we can kind of go from our predicate alpha directly to the class of models of our theory, simply by saying, well, all these structures that satisfy the axiom or our set-vertical predicate are the class of our model. Yeah? And then we can do different things with our class of models. Or if we are even a bit stricter in the formal level, we could also say that our whole structure is, in the end, completely built on our domain or the principal base sets just by using Cartesian products and power set operations. This is how structures are defined in mathematics and also model theory. And then we can say that this structure here is always kind of a definite construction rule based on the domain. And used by semi-Frankfurt gap theory, we can say that's not a class of models, but it's even a set of models. Yeah, it's really important at a later stage. Yeah, but then we have to fix our domain. Yeah, that's an important thing. Okay, that's not all. We also need to further ingredients at least. On the one hand, we need a scope of intended applications, because we cannot simply say, well, our theory is about these models, because then we won't have any way to refute our theory. Yeah, so we need at least a different specification of what's our theory about. So we have to indicate somehow what's the intended applications, here denoted by I. And what's, in my view, the most important point and the most beneficial point of a structural view, not in the piece version, but in the later developed versions, the concept of admissible blurs. So the idea there, I will introduce this concept later, that for every structure here, we will have a kind of a blur that's directly, based on the theory and the idealizations that are in the theory, and so it provides us with a way of a metric or topology which will help us to define what means close enough and good enough. So that's why I'm a strong supporter of this view on theories. Yeah. Okay, let's go to the first lesson. So what is now this uniform structure of the admissible blurs? We usually have kind of a theoretical relation. We have some data points, and the common case is that not all data points are exactly on this relationship. Yeah? So differ a bit. It's not a problem. Usually we have kind of the concept of these error bars here in both directions, and even though they not always fit to the line, it's always not such a problem. Yeah. So there's one way to handle it. On the other hand, we also consider different theories with the same scope of application, and also there we'll find discrepancies. Yeah? So for example, here is ideal gas theory and one real gas theory. In one part, they make almost the same predictions. In other parts, they make different predictions. We also would like to have here kind of a measure to say how much one theory deviates from the other. Yeah? And yeah, the concept of a blur is kind of the smearing of our theoretical relation. Yeah, it must not or doesn't have to be symmetrical, can be a bit different at certain points. And if we can introduce such a concept, it will solve both problems. Yeah, then we can discuss how we can talk about whether one theory is more accurate than the other one, and we can also discuss the confirmation of theories, even though there is no exact match between theory and data points. Yeah. And if you now look into textbooks on topology, you'll find the concept of uniform structures. Here's the theoretical line there, and the shaded arrow is basically the blur. Yeah, and the idea is to use this concept then to define admissible blurs for our theories and to have for all our relationships kind of these blurs, and these will do all this stuff that we need to. Yeah. So the topological definition for uniform structures comes from Bobaki from the 1970s. What's important here, so the U is a blur here, in this picture is a V. We require that the diagonal line there is always inside every U. There's also a form of a symmetry condition. So for every V or U, we find also the mirrored version of it. So if we mirror it along this line, will be also a blur then. And also we can construct Corver blurs from blurs that we already know. So if we have a blur in our uniform structure, we can, or we are sure that every set that's a superset of this blur is also a blur. And there are also rules to construct finer blurs. If you have two blurs, the intersection will be a blur. Yeah, so it will always be guaranteed this is satisfied here. And the last axiom there is basically that for every blur, we find a blur that fits twice into it. Yeah, that's a bit abstract there. So the intended interpretation is the following, that we read UXY as X is empirically indistinguishable from Y. Yeah, so these axioms now are not, not adequate for expressing this for several reasons. First of all, if you want to have this as a symmetrical condition here, that X is empirically indistinguishable from Y, exactly when Y is empirically indistinguishable from X, is not satisfied by this condition, because we then would need the symmetry in U and not in phi here. Yeah, so it's simply the wrong stage there. On the other hand, it's clear that when I have a blur that's satisfying that all our data point and theory confirm, so it's broad enough, that every Corver blur will have the same property. Yeah? But on the other hand, it's not clear that every finer blur will also save the data. Yeah? So there's a distinction between this form of defining Corver blurs and defining finer blurs, which is not covered here in this axioms yet. Yeah? So we will need some further structure there. Yes, and also this might not be the case. Yeah, so especially if you have a phenomenological law, we are pretty sure there is a lower limit of accuracy. Yeah? So we will need some further axioms in order to really come to admissible blurs for our empirical theories. Yeah, so but we start with this is axioms from the slide. So we will say admissible blurs will be a subset of a uniform structure, a non-anti-subset, of course. So then we simply say now we want the symmetry in the right form, so in U and not in A or phi. And then comes the novel part. So as I said, we want to somehow express that if we have an empirically successful blur, that this property is maintained when we proceed to Corver blurs. Yeah, so I somehow need a new relationship here, I call it S, like success, for an application of the theory and a given blur. It means simply, yes, the measured value, or no, the predicted value from the theory xi is within the blur of the empirical result. Yeah? And so that's simply set by this condition here. And then, as I said, it would be quite nice to have a lower bound, especially also to compare different theories, because then we can, for example, compare real gap theory and ideal gap theory and say, well, the lower bound of the real gap theory is lower, and this is just a better theory for this domain. Yeah, so it's basically the finest blur that still is capable of saving the theory for some applications. Yeah. And similarly, we also would like to have an upper bound for a blur, because by the third axiom here, you can always proceed to Corner blur. So in the end, we could also have smearing our vertical relation over the whole set of values. So every point would be indistinguishable from every other one, which of course not something that would be helpful for any empirical application. So we need kind of an upper limit that says it's the least accuracy that we want to have. Yeah. So that should be also there. So it's simply defined by pragmatic reasons, which accuracy we want to have. We can also set it always to the lower bound, of course, if we want to have the best accuracy that we can get. Yeah, then we also have to require that every of our admissible blurs is bounded from bar. Yeah? So in fact, these last two requirements are not my own. They are already demanded by Balsam, Leaders, and Snead in their architecture for science, but the other four conditions are kind of added to this concept. And maybe you are now a bit puzzled. What does all this do? So, for example, how can we, use this? Yeah, so it looks like a nice formal framework, but how should we apply this? And also, is it not, easier alternatives? Yeah, people would usually start with metrics, for example, not the uniform space. First, for the first point, often, I think in most cases, we can kind of, at least get an idea of the general form of the uniform structure from the theory itself. So if we, for example, consider the factor which is fluctuations scale. Yeah, so in some cases in statistical mechanics, we usually have 1 over square root of n, for example. And so 1 over square root would be the right form of the admissible blur then. Yeah, or if we have some geometrical projections, we can directly say from this projections would be the appropriate blurs that we, or forms of the blurs that we would use. And then when we discuss, what are the lower bounds that we need for our theory, depends now on the stage of the theory development that we are. Yeah? So initially, when we have just the first data point and have the very large uncertainties, we cannot say much about the lower bounds. But as soon as we come to points where the uncertainties from measurement and from statistics are not large enough to explain the discrepancy between the law of functions, the theoretical predictions, and the data, we can already say at least the lower bound has to cover for this difference there. Yeah. And at a later stage, as soon as we are able to derive this theory that we are now discussing from a more fundamental one, we will see from the derivation and the approximation that take place within the which we can at least estimate some parts of the lower bound there. Yeah. And now the second question, why don't we use different formal concepts? We could use a more specific one of metrics or more general one of topologies. Yeah, maybe first to the second one. Topology can define closeness, of course. Yeah, so neighborhoods, but this cannot define relative closeness. So we cannot define within the topology X is closer to theory T than to theory T prime, for example. Yeah, and that's something that we really want to have. Yeah, so that's why general topology is not what we can use for metric. I mean, it's a bit more difficult to connect the axioms of matrix directly to the idea of indistinguishability. And on the other hand, at least for metrics that are induced by norms, we have a translational invariance. Yeah, so we have these two relations here. So on the one side, we have the symmetry here that x will always have the same distance to the point above as to the point below. And for some cases in physics, for example, for phase transitions, it's not really useful. Yeah? For example, if I have a sample of water with 0.5 degrees Celsius, and I know, well, my temperature is plus or minus 2 degrees. I still know if my water is liquid, that it's not minus 1.5 degrees. Whereas I'm not sure that might be 2.5 degrees. Yeah, there's some phenomena in physics where we don't want to have this symmetry here. Yeah, and also, I mean, this looks really awkward. No? So, of course, if we are really high numbers, the difference by 1 is has a completely different meaning than for small differences. Yeah, here, of course, we could simply change from absolute differences to relative differences. It's not the same problem as this one, but that cannot be solved this way. Yeah. So in fact, we could use different metrics that are not translational invariant, but in this case, we kind of lose the advantage of metrics that we have first place, because I mean the metrics that we usually use are kind of Euclidean metrics or norm-induced metrics, and yeah, this advantage of being used to them and being quite handy is lost when we go to non-standard metrics. Yeah. But anyway, every metric has a corresponding uniform structure, so we could always use a metric. Yeah, and so in most applications, people will define a metric that fits to the problem. Yeah, so what I say here, and then use this for the uniform structure. Good. So what does the concept of optimizable blurs now accomplish? So we can express what approximate means for theoretical claims. Yeah, so we can write down a theoretical relation, and then say, this is what I do here on the next slide. This is my theoretical relation, and now I say, well, it's satisfied for all x that are within the blur close to this x prime. Yeah. So since we have this upper bound, we can also distinguish between appropriate approximations and not too much distortive idealizations from approximations are too coarse, that are not adequate for our problem. On the other hand, since I do not just define one blur, but a set of admissible blurs, we can, or we have at least, the possibility to use different blurs for different applications. Just for example, if some applications I need very precise values for in the high domain, or I don't care so much about the lower domain. In other applications, it's very important to have a very precise values in the lower domain, so I can use different blurs. Yeah, it's possible here. And since we have the relative closeness here, we can compare different theories or approximations and say which one is the better one in this sense. Yeah. And in the last formal advantage, since all our theoretical terms in the structural view are composed by Cartesian products and power sets on our base sets, we can also induce a uniform structure from our base terms on the other ones, because a Cartesian product on a uniform space gives us a new uniform space, the same with the power set. Yeah, so we don't have to define for every theoretical term that we have a new uniform structure if we already have uniform structures on our base sets. Yeah, they get induced on the other terms, which makes it easier than if you have to apply this. Good. Okay, so if you now compare this with the concept of approximate truth, I would say we have here something that very well expresses what we mean with empirical adequacy. Yeah. But this is not the same with approximate truth as Laurent argued. A realist would never want to say that the theory was approximately true if its central theoretical terms failed to refer. If there were nothing like genes, a genetic theory, no matter how well confirmed it was, would not be approximately true. Yeah, so we need, of course, empirical adequacy, but it's alone is not enough. Yeah, so one proposal how one might still use admissible blurs to define approximate truth would be to have also the concept of approximate representation. Yeah, and so I won't go into details, but I mean, basically, it's the standard way how to define representation in terms of models and the system. And the only thing is here, I would say we have also a model with the theoretical properties and the system with some measurable properties. And we will then simply demand that the theoretical properties and the measured properties are then within the same blur, in one neighborhood. And so we could define something like an approximate representation. Okay, if it's enough, I don't know. That's why I had a question mark behind the first lesson. But I'm pretty confident that we can use this concept to define limiting case reduction of theories. And I think it will be pretty straightforward how to proceed now. So what is limiting case reduction? I think everyone who works in physics knows it pretty well, because basically every relationship between different theories will find one way of limiting case reduction. But if you look into the philosophical literature on it, it's not very specific about what it actually means. Yeah, so of course we can write down something like this, but as long as we don't have specified what TF and TC are, or which kind of objects, and I mean, what should this mean here then? Mm-hmm. Yeah, so we need at least clarity about what is a theory, and also then what is the right topology to compare to the theories. And here, kind of from Betterman's book, yeah, so it must be taken with a grain of salt, and we cannot assume that this falls for every equation of TF and TC. I mean, it's not really helpful to understand what it means. Yeah. I will only sketch now what the road is, but I think you can imagine. So we go now to the set of models. So M prime will be our TF here. Yeah, and basically the parameter that will be our limit parameter is called B. So we have within M prime axiom kind of a term that just says, well, there's B, and B is a variable, but there are some values excluded, especially B0. Yeah. And the theory that we want to compare it with is M1, and M1 usually doesn't have contains B already. Yeah? So that's pretty usual here. For example, when we look at these examples, classical mechanics, for example, doesn't have the speed of light as a essential parameter in this theory. Yeah? So this should be simply added to this theory in order to make it of the same structure as M prime. Yeah? So usually we also need much more changes to the theory, but basically we bring M1 into the same mathematical structure as M prime. Yeah? In some cases it's easier. So here, for example, in this case, it's not as difficult as it would be for the quantum case here. Yeah, so here we have completely different mathematical structures, and it will not be possible to do this so rigorously as we can do here, for example. Yeah. So here we will basically only have kind of partial relationships. We will never completely recover classical mechanics if we stay within Hilbert space formulas. But as long as we can do it, then we have here like one space, and basically and simply have to compare two sets. Yeah. So what's clear by this demand that on the one hand we have B as a parameter of our theory. It's forbidden at B0. On the other hand, we have this theory. It does not depend on B, but we simply add it as a meaningless parameter, but we of course have to add to the axiom then that it assumes this forbidden value B0, which will be our limit value then. Yeah, so it could be 0 or infinity usually. Yeah, and then of course because of this difference here in the axiom, we will have that there's no there we are. There's no intersection point between them. Yeah, but if we conduct this, we will find topological relationship between the two. So the set of models of our reduced or limiting case theory will be at the outer rim of the models M prime. So it's not apparent how this is related to a limiting case, but we can have a partition of M prime by all different values of B. Yeah, so we can have possibly here infinite set of different B's and can have a partition that every shell here will have a fixed value for B. Yeah, and then we can rigorously define what does this mean here. Yeah, so each shell or the shells of M prime for different B's can then be defined within a uniform space defined here on M prime set, and then we can make sense of this equation. There are some further conditions that I can mention in the Q&A.
M1 is subset in the middle. M1 is subset of.
M1 is a different theory. So we have M prime as one theory.
The fourth line, what does that say? M1 is a subset of. Do you mean M dash?
Which one? Sorry, which line?
Fourth line.
This one?
M1 is a subset of.
M0 is a superset here. The space in which we discuss everything.
But then you have M0.
M0 is
with M1 is has no intersection.
No, oh sorry, that's wrong. Yeah, this should be M prime. Yeah, it must be M prime, sorry. Yeah. Otherwise it can't be.
But and the first one was what? The first one, M1 is
M1 is a set of models of the limiting case theory.
What was M0?
M0 is a subset here, the space in which we discuss everything.
The superset.
Yeah.
Okay. Not as just a universe of this part.
Yeah.
Okay.
It's around here. So basically a set to which we can extend the uniform structure.
I thought it's topological inside.
No.
Open subset. Okay.
Okay. So again, what is good for? We can in fact learn different things from it. First of all, that two different the relationships that are usually not distinguished are in fact something different. Can be easily explained on again in the example of the graph theories. Namely, we have on the one hand a relationship that if we let the van der Waals constants go to 0, that we have on the whole domain of volumes and pressures that our isotherms approach. Yeah. On the other hand, for all values of A and B, so also non-zero values, we always find a volume for which the van der Waals theory and the ideal gas theory kind of approximate. Yeah? So symptotically approximate. And these are different relationships. Yeah? And they are also kind of independent of each other. Yeah? And there are some places in the discussion where they are even mixed up and lead to two problems. Yeah? Okay. Last one. Maybe skip a bit. Directly come to maybe one last interesting thing that was also asked yesterday in the dinner about why or maybe a concrete case where we can really talk about what is real then, namely are phase transitions real? So first question would be, what are phase transitions? So phase transitions are melting and boiling, freezing of material. If we look on it in a phase space, and we would now plot some properties of the system, like for example density, we will see it changes a bit here. If I just change the temperature and keep the pressure constant, and then here along the line of the phase transition, there will be a jump. Yeah, so it will be go up, then will be go down a bit, and then here will be next jump. Yeah, so I mean, since most processes in nature are continuous, these are very interesting anyways. And now the question is, why shouldn't they be real? So what could be the reason here? And the argument here is the paradox of phase transitions. That's interestingly not only discussed in philosophy of physics, but also in physics itself. So it's usually either discussed in physics or in philosophy of physics, but here we found it in Borg. So what's the problem here? So in classical or also quantum statistical mechanics, the partition function is a sum of exponential functions, and so it can never be zero or singular. It's always an analytical function. Yeah? Then this definition of phase transitions in statistical mechanics will say, I mean, this will never happen. Yeah. I mean, this might make sense because we want to have some jumps, some singularities, so we need zeros or singularities of the partition. And so some might, some might say, well, that's pretty easy. Then we simply have to say statistical mechanics can simply not describe phase transitions. But the opposite is true. We just have to use mathematical tricks, namely, for example, letting the size of the system go to infinite, and then we can use statistical mechanics to really describe every phase transition we know, precisely. That's the reason why. I mean, that's a problematic step to say, well, phase transitions cannot be described by classical mechanics. One solution would be then to say, well, 2 is wrong. Yeah, so there are no real phase transitions or phase transitions in the real systems. These are simply a theoretical concept which does not apply. So only in idealized systems. So the reason why it might be the case that they are not real. That's, however, not my solution. I say there is no paradox at all. Because if you look at these different claims here or statements, there's no connection basically between 1, 2, and 3, 4. Yeah, here in 1, 2, we are talking about real systems, so empirical systems. In 3, 4, we are talking about theoretical models that represent these systems. Yeah, so without any representation assumption, there is no connection between those two, and so we can keep all 4 of them. We simply need a representation assumption that does not lead to a case that if we have an infinite model, that we cannot represent it for a final system. Yeah? And with the concept of representation that I mentioned earlier, we can have this. Yeah? And so we can save we can avoid the paradox of phase transitions. We can also save statistical mechanics. We don't need any different definition for phase transitions, but still have real systems that have phase transitions. But at the cost, of course, then we cannot interpret statistical mechanics in a realistic way, because we need this infinite idealization. Yeah. Okay, that's all my conclusion. I hope that you don't feel like this poor guy now.